Hello and welcome to today's video. In this video, we're going to talk about an integration rule. That is the rule called integration by parts. So the title of today's video is Integration by Parts. Now the idea of that rule is pretty easy. We have already learned that integration basically is the reverse of differentiation. So if you want to integrate a function, then we need to find an antiderivative. That is, a function that differentiated yields the integrand. When we discussed differentiation, you will hopefully remember that we encountered a few differentiation rules. And some of these rules can be transformed into integration counterparts. And that is how you get the integration by parts rule. The idea here is to take the product rule and transform that into a corresponding integration rule. So what we are going to do now is we're going to transfer the product rule of differentiation into the integration setup. Remember that product rule works like this. You have a function that is composed of two functions f and g, which are multiplied, and you want to differentiate that product. Now what you have to do then is you differentiate f, multiply that with g, and then you add f times the derivative of g. And if you just integrate that, basically what that means is that the function f times g is an antiderivative of the right-hand side. So what we can say is this is the same as the integral of f prime times g plus the integral of f times g prime. And if you solve this for that integral, then you get the well-known integration by parts formula. And let's formulate that as a theorem. So that is the integration by parts formula. What we need to apply that is an open interval as usual, and functions f and g that are differentiable on an interval. A little more, they need to be continuously differentiable. So let I subset of R be an open interval, and let f and g, functions mapping from I to R, be continuously differentiable. Then the following integration rule holds. That is the integration by parts rule. The integral of f prime of x times g of x dx is equal to f of x times g of x minus the integral of f of x times g prime of x dx. And of course that can also be applied to integrals with bounds. So if we have a, b in that interval I, we get the corresponding rule. The integral of f prime times g from a to b is the same as the function f times g evaluated at these bounds minus the integral of f times g prime again from A to B. Now, what use is a rule like this? Yeah, you might argue, well, we have a product of two functions here. We have a product of two functions here. It's not really a lot that changed here. But basically what you can do is you can make a trade-off. You get to differentiate one function, you have to integrate another. F is being integrated here and here. G is being differentiated. So if it's easy to integrate this f prime function, then this might be a trade-off that is worth the cost. And we'll see a few examples that demonstrate how to use this integration by parts rule. So let's have a look at examples. First example, let's consider the integral of the logarithm ln of x. How do we compute that? Well, we don't really know how to integrate the ln, do we? Well, that's a simple trick here. What we do know is how to integrate the constant function 1. And what we also know is how to differentiate the ln. So we can write this integral in the form 1 times ln in the integrand. And then we use 1 as our function f prime, and the ln is our function g. So if we now apply this integration by parts rule here, we have to integrate f prime. That's easy. And we have to differentiate the ln, g. Well, that's also easy. We know how to differentiate the ln, right? So let's do that. What do we get if we do that? Well, here, first, remember, we have the product of f and g. So we have to integrate f. Well, one integrated is just x. And we leave the ln untouched. So that's the first part. This is the f times g part. And then we have to subtract f times g prime. So this is the integral. Well, f, we already did that. That is x, and g prime, well, differentiating the ln yields 1 over x. And now things fall into place. That means what we have here, so this is, again, this is f, this is g prime. What we have here is x ln x minus the integral of x divided by x. Well, that's 1. And again, the integral of 1 is something that we can compute. So what we get is x ln x minus x. And of course, as usual with indefinite integrals, we can't add any constant. We have to add a constant to get all possible antiderivatives here. So this is how you can compute the integral of the ln using integration by parts. Neat little trick. I'll show you one more neat little trick. That's also something that you'll frequently encounter when you do integration by parts. And for that, we'll consider the following example. We want to compute the integral of sine times cosine. And again, what we do is we take one of these functions, let's say the sine, as our function f, and we take the other as our function g. So in this case, we have sine is f prime, cosine is g. Now if we apply the integration by parts rule to this, we first need f times g. Now what is the integral of the sine? Well, as you know, cosine prime is equal to minus the sine. So if you want to integrate the sine, then we have to use minus cosine, right? So this is minus cosine x times cosine x. Well, this is g, this is f. And now we have to subtract f times g prime. Again, f is minus the cosine of x. And g prime, well, if we differentiate the cosine, then we get minus the sine. We know that already. So let's deal with all these minus signs here. Here we have minus cosine squared. And here we have, let's see, minus, minus, minus. So altogether that's a minus integral of, let's swap the order as well, sine x cosine x dx. Now what do we gain from that? Basically we're back to where we started, right? So this is sine x cosine x, this is the original integral. We did a pretty useless reformulation here, you might think, but if you look at that more closely, you can see that actually what we have one is an equation. So here's our equation. We have sine x cosine x integral equals minus cosine squared x minus this integral once again. And what we can do now is we can just solve this for the integral. So we take this, we add it on both sides, and then we just divide by 2. And that yields sine x cosine x dx equals minus 1 over 2 cosine squared x. And of course, again, we need to add a constant for the indefinite integral here. So this is how we can integrate an expression like that. And again, as you have seen, integration by parts might lead to the original integral reproducing, but in some cases that is still a good thing because you can solve the equation for that original integral and ultimately obtain a solution doing that. So this concludes this introduction into integration by parts. As usual, we'll see more examples in the exercises. And as usual, I hope we'll see you in one of the upcoming videos when we talk about more integration rules. So I'll see you then.